There are two things that are going to happen in this section. All of the problems that you had before from yesterday's lecture were problems where you were bound by an axis and then you were rotating or revolving around that axis. So you were either, it was the curve, the x-axis, and then you were rotating around the x-axis, or the curve, the y-axis, and you were rotating around the y-axis. The difference in these problems is you're going to be bound by a curve, a line, a horizontal or vertical line, and then you're going to revolve around that horizontal or vertical line. So literally, basically, we're taking the problems from yesterday and we're just shifting them somewhere else in space. We do have a formula for that. I'll go back up. This is where that formula is. We're going to see why it works, and you can always visualize this like it should make sense. You're going to see the radius of your thing that you are rotating is your function value, but this time minus c. So we're just going to have an extra constant in our radius term, and we're still going to integrate pi r squared h. Same thing we were doing yesterday. This formula is the same formula as yesterday because you are either rotating about the line y equals 0 or x equals 0, because those are the equations of the two axes, right? If you plug a 0 into this is yesterday's formula. And that was the idea that I was saying. The master formula that we're going to learn by the end of F8 is just more things going on, but every one of these formulas comes from the master formula. Pi is there because we're integrating pi r squared h. Okay. The other thing, too, about this formula, and really anytime you've got something being squared, we may, when we visualize our things, see that our radius is f of x minus c. We may, when we visualize them, see that our radius is c minus f of x. It may go both ways. It really just depends on how the problem is set up. Actually, I think it probably has to do with whether your c is positive or negative. But again, we'll see it when we do it. It doesn't matter which one you put in this formula because that thing is being squared before anything else. So whether you have the correct radius or maybe the negative version of it instead, that part won't matter because it's being squared before it's integrated. So squaring it, if you happen to have a negative number there, doesn't matter. So just kind of a feature of these problems. And that means you can just strictly use this formula. You don't, you're not going to lose points because your radius is negative because it's known that it's being squared. Okay. All right, so taking a look at example 6, I think we have to sketch all of these. We have y equals 3 minus x squared and y equals 2. So we want to find what that looks like. That is not a pen. So we'll draw on my x and y axis. 3 minus x squared is a downward facing parabola that goes through the y axis at 3. Oh man, my right side looked good. My left side looked terrible. A little bit better. And then the line y equals 2 is this. That is the line we're revolving around. So we have now a shape in space instead of just being locked into an axis, but it is this area right here that we want to rotate, but we're not finding that area. We're trying to rotate. This is not going to be good. I'm going to do this. There we go. That's what I want. Cool. My parabola didn't exactly hit 3. Oops. There we go. Now it does. Where does that parabola intersect the line y equals 2? It does at 3 minus x squared equals 2. But you actually can, if you think about it for a minute, you might actually be able to get those numbers without doing any solving. When does 3 minus x squared equal 2? Yeah, when x equals 1, right? X equals 1 and x equals negative 1, because you can see it's pretty much symmetrical. So yeah, so those x values are x equals 1 and negative 1. You can find them either way. You can set 3 minus x squared equal to 2 and solve, or you can just kind of reason through it and find out that the x values here are 1 and negative 1. All right. So again, we're getting some sort of three-dimensional shape that gets bigger as it gets closer to the origin and gets smaller as it gets further away from the origin. I was looking at my video, the pictures in my video from last year, and I feel like I used to be able to do this well. I don't know. Yeah, right? And I just don't feel like I'm doing it well anymore. I don't know. Maybe I should have practiced. Still doesn't look good. This one should be smaller than that one. I know, right? So we have this, circular shape that if you were to trace it on any spot of it, it would feel like that. Using our volume let's talk about what the radius of that shape is. The radius of the shape at any given point is that length, agreed? So what is that? That is f of x, but it's too short of the f of x. So the black line is, so the blue line plus the black line is f of x, right? So the black line alone is the f of x minus 2, because that horizontal line is at the value of 2. So in this case, our r for radius, do it in the color coding, our r is 2 minus f of x. Sorry. Boom. So then again, we're just integrating pi r squared. It's not 2 minus f of x. I keep jumping ahead of this, a step ahead of me. It's f of x minus 2. Yeah. So yeah. Because it's the whole line, the blue plus black is f of x. So the black line itself is f of x minus 2. And you're right, it also doesn't matter. But I want to, if I'm saying the radius is, I want to say the right thing. But you are 100% right. It doesn't matter. Both integrals will come out the same. So we've got pi times the integral from -1 to 1 of radius squared, f of x minus 2, but squared, times the height, which is dx. And my f of x, of course, is 3 minus x squared. So I can do 3 minus x squared minus 2 dx. And square it like it was before. Okay. So matter of solving that integral. I don't see a reason to waste time actually doing that in any other way than using a calculator. So grab your calculators, put that in. Don't forget the pi out front. Second pi, alpha f4, f2, -1, 2, 1, parentheses, 3 minus x. What I got? Yeah, answer ends up being about 3.351. If you did have to do this by hand, I would have collected like terms before I did that. So I realized that when I started typing it into the calculator. So this is really the same as -1 to 1 of 1 minus x squared, but squared dx, because you can collect the 3 minus 2. And then, that's going to save you 2 plugins if you just went and found the or if the FOIL. No, I'm sorry, that would save you a bunch in foiling. That would be like, you have to do like a 3-way multiplication versus a 2-way multiplication. All right, letter B. Yep. Y equals the square root of x y equals 0 and x equals 4. Let's see what happens here. So we got to remember what the square root of x looks like. It's just a parabola flipped on its side, but only the positive part of that parabola. That was going to be nice, and I hit the erase button. So you're drawing x squared, but you're drawing it on its side, but you're not drawing it in any negative y values because the square root of x is only positive. Oh, okay. We want this. X equals 4. Gotcha. Yes. What do you mean, does I have an integral? There's a whole section, there's a whole field devoted for doing calculus with, yeah. Yep. Most of it works the way you would expect it to. Mm-hmm. All right, so we've got x equals 4 and y equals 0. We are rotating about the line x equals 4. So if I'm rotating across a line that's vertical, like the y-axis, what do I need my function in terms of? Y's, right? Yeah. So we should be in a dy situation. So we have to take y equals square root of x and rewrite it as x equals y squared. We've got to use y values. So this is clearly 0. That's why they gave us y equals 0 in our problem. That's a bound. And what's the point here? 4 comma. Nope. Hey, good morning. Were you here?
Yeah. We're talking to Miss River.
Gotcha. Cool. And did you catch McSwiggan / Wintermantle? They're looking for you. They want your digits. Okay. Cool. So it is not 16. It is 2, yeah. The function we're graphing here, the function that we're graphing here is y equals the square root of x. So you want to plug that 4 into the square root of x. So that is 4, 2. And again, since we're doing a dy, since we're rotating around a vertical line, that's the number we're going to need to integrate from. Again, same idea. We're looking for the radius of any one of these disks. Maybe I'll just draw one in and try my luck this way. So we're looking for the radius of one of these disks. Aha, and this is the one where it's going to happen the other way around. So if I wanted to write the radius, I switched the colors that I used last time. The entire line is 4, and the black line is so the whole line would be 4 from here to here. And how would I measure the length of the black line? It is definitely a function, but now I think in this one we don't have a function defined, so we have to figure out what that function is. What is 4 minus something? When we change to y, the axes change their meanings. We're used to plugging in values of x to figure out y's. But when we're thinking in terms this way, we are thinking about plugging in y's to get x's. So if I'm here, I have some y value, and I want to know what the corresponding x value is. What do I have to do with the y to get the x square it, right? I use this function. My function is y squared. Wherever I am on the y-axis, to figure out the length of that black line, which gets me exactly to the curve, I've got to square my y to get my x. That's really the same issue we had with putting in this point here, right? When I was saying it's 4 comma what, we were really doing the problem backwards. I was asking myself, what number do I have to plug in to get that x? So that's the idea. This is y squared. Whatever your y value is, you need to square it to figure out the length of that line. If you're at 0, the line is, there is no black line. If you're at 2, the black line is 4 squared. Square it to get it. If you're anywhere in the middle, square it to figure out where your line is. So it is 4 minus x squared. 4 minus y squared. Y squared, right? To get the x position, we do y squared. We are trying to figure out the length of the blue line. The blue line is the entire 4. Any y level you're at, the whole thing is 4, right? But the radius of your disk takes away the function value.
One other thing.
Are you saying you could have just written the integral without thinking about it? Is that what you're saying? Oh yeah, no, I'm not disagreeing with that. But understanding is important too. Because what ends up happening is people are blind. What ends up happening is people blindly follow formulas and start using the wrong formulas in the wrong spots. Which is why I go with the explanation. I know I'm right when I can visualize why everything in my formula is the way it is. Yeah, right. That's my goal with that. I mean, I could teach a million formulas. We could just go formula by formula, but knowing why things work can help you remember them when you didn't just do it 3 days ago, and help you distinguish what should I be doing in this situation. So my radius, the radius of that disk that I showed, is a big line, which is 4, minus y squared, because it's the function that's being removed from it. So we're ready to write our integral. Same idea. It's going to be pi, the integral from 0 to 2, perfect. 4 minus y squared, that's the radius, but squared, times the height, which is dy. When you go to type that in your calculator, there's nothing saying that you have to use y's, right? We're using y's because it matches our picture, but you can totally just use your x button because it's easier. So go ahead and find out what that is. 0 to 2, 4 minus x squared. But squared. Alrighty. I got 17.067. You do, yeah. I didn't get 17.067. I should have realized, actually, it was a repeating 6, and it should have hit me that I didn't multiply by pi, because how would it be? Yep, 53.617. Boom. Cool. All right. And let's see, last but not least, letter C. All righty. We have the function y equals 2 to the x, but minus 3. That looks like any other exponential function, except it goes through the y-axis at -3. Or sorry, no. Where does it go through the y-axis at? Not +3. When I plug 0 into that function, what do I get? I don't get 1, I get -2, right? So the y-intercept of an exponential function without anything after it would be 1. So when you subtract 3 from it, that actually drops you down to -2. So unlike polynomials where the y-intercept is just easy, you actually have to basically add 1 to what you see there. So this thing is going through the y-axis at -2. We actually also have the line y equals -2, so that's kind of built into this problem. So here's y equals -2. Our exponential function looks like this. And we want x equals 3. Just for sketching purposes, that's actually going to go through at 3, 5. So I'm going to go ahead and draw it somewhere over here where it looks like it's gone pretty high. This would be 3, -2. And this is -2, not -2, 0, -2. That's what I was looking for. Knew something was off. Boom. Okay. So again, we are rotating about that line. So we are trying to make a shape that loosely looks like a cone, except it's got a very curvy side instead of a straight diagonal side. Any given disk here would look like this. And its radius, I feel like this is really similar to our last one. Its radius would be but this one, if you this one to kind of be tricky. If you want to keep your radius positive, you would want to say 2, right? Because my whole line is 2. Got a little bit bigger. And we want to take away the function value, right? But the function value is negative. Well, then that would actually, because that'd be less than 0. It already is negative. So the radius here actually is 2 plus f of x. We've basically flipped both things signs. The y value is -2. The function value is negative. So if I take a 2 and add a negative function value to it, that's going to take 2 and take away that function value. Take away the amount that function value is. And then that's the thing that we have to square. Which ends up just being what our formula asks us for. If we use the formula, we would be doing f of x minus -2, right? Yeah. So it ends up being the same thing because we would just write f of x plus 2. So again, using the formula, and then we'll finish off here. I'm integrating from what to what? 0 to 3. I'm going to remember to write my pi. I'm going to remember to type my pi in my calculator. I'm not going to do 2 plus f of x. I'm going to do 2 plus 2 to the x minus 3. That can be in any order. The 2 could come first. The 2 can come second. I'm going to square it. I'm going to dx it. I'm going to simplify it this time before I put it in my calculator. I should have -1 plus 2 to the x, but squared dx. Save myself a couple button presses. Integrate from 0 to 3. Got -1 plus 2 raised to the x. Square it, dx it, pi it. 88.741. Yep. Nothing exciting about these answers. Great, 88.741. Yeah. All right. So yeah. Your goal is to get the question right. There's never a time where they're asking you to draw it and judging the picture that you draw. There's never a time where I'm going to ask you to draw it and judge the picture that you draw. But that, I mean, sometimes to figure out the limits, to figure out what's going on, a drawing can help. I'm not sure if there's a little bit of work there to kind of do all of that in your head, but you know, do you have to draw it? I would draw it, yes, but do I have to think through what the radius is? Not necessarily follow the formula. Yep, that'd be my answer to that one. Cool. All righty. So with that, you guys have the rest of the time.